So good afternoon and welcome to today's lecture. It's going to be a little bit different today because I am going to do a couple of examples from last week's material to start with. As I already told you, week 2 is like really overcrowded with all the parts from chapter 10, and you may have some difficulties with that. So I'm going to start with a couple of examples from last week's material. Before I do that, let me go to the questions that I got either via email or via the bulletin board that we have on Canvas. So on Canvas, as you know, precisely at the position where you find the link to the YouTube stream, there's also an option to ask questions there, and there were a couple of them. So one of the things is during the tests you will have no calculator. So you may have heard differently, but not a single calculator, not a simple calculator, not a graphing calculator. You can just use pen and paper during the tests. All the tests are going to be online, so nothing's going to take place on campus. It will always be you behind your computer. There will be proctoring, so you will get more information, but there will be proctoring using a system that's called Proctorio, which basically means that we can see you while you're taking the test, and that is just to prevent all of you from being together and sharing your answers during the test. I mean, that's of course very nice if you could work together, but that's not what we really want to do. So let's see. I'm getting a bit of a strange message on my screen here. Let me just check if the stream's still going. It is, so that's fine. Okay. Also, the midterm test, you will have access to all the exams, so you can see the type of questions we ask you, and there will be more information there. So you will have more information on how the test will proceed. It is going to be in week 5. We currently start in week 3. And in week 5, you will have a test either on Thursday or on Friday. You will get the details. It is online, so you don't need to come to Eindhoven. And the material during the test will be weeks 1, 2, and 3. So everything we have covered in the past weeks, plus what we will see this week, that is what will be in the test. I also had a question in the homework and maybe also in the online test, I'm not quite sure. There is a couple of questions on determinants, but I didn't cover them, and determinants you can just skip them. So they don't belong to the material. You don't need to know what a determinant is. Then finally, the online test. As you know, we currently have the online test also going, and they also are part of your final mark for the course. The online test, you don't need to have to do them in one go. So you can do a couple of questions and just log out of the system and return later and continue where you were and redo a question if you didn't manage to do it the first time and you only got part of the marks there. So you can go back there. So let me see. I think that's most of the questions that I got either via email or via the online system. If you have further questions, use the chat and I will look at it in the break, so at 2:15. Or use the Canvas system to ask me questions before lectures. I always check it if I don't forget, but otherwise please remind me. And I'll try to answer your questions like that. So as I said, I'm not immediately going to the week 3 material yet. I would first like to go back to the week 2 material. And in week 2, we were talking about this. So we have been talking about vectors and about lines and about planes in 2 and 3 dimensional space. And we have seen that if you have a point, basically you specify the x, y, z coordinate and you have some point that is fixed in space. Yeah. Then if you have a line, you can write that in 3D space as a vector equation, which basically means that a line consists of all those points x, y, z in space that originate at some point. So this should be a point that is on your line, plus some multiple lambda here, Greek letter lambda, so Greek letter for L, that is the small letter, times a direction vector. So the 1, 0, 1 here is the direction vector, and it just means which way you're traveling along the line. So we're in 3-dimensional space, we're at some point, And we can travel either in this direction or we can travel in that direction. Then for a plane, you have two options we have seen. So the first one is this thing, and that is called a vector equation, just like we had for a line. And it works the same way. So we have all points x, y, z in space. And then we take some point that is on the line. And now we have basically two direction vectors, you could say. 1, 0, 1 and 3, 4, 5. And you multiply them with arbitrary numbers. And here I used Greek letters lambda and mu. So a plane in three-dimensional space, that is basically like a sheet of paper. So it is very thin, it doesn't have any thickness, and it extends in all directions. So in all directions it goes to infinity. And as we have seen last week, you can also describe a plane in this form here. So what we have here is an equation, and it basically says all points x, y, and z are in the plane that satisfy this equation. And you can see that if you choose x and y, then the third coordinate is fixed. And that makes sense for a plane, right? And what we've also seen last week is the coefficients. So the 2, the 1, and the -2 here, they form a normal vector. So if you would build the vector, and I call it n here, with components 2, 1, and -2, then basically what we have is in three-dimensional space, we have some plane. So let me plot it like this. So it extends in all directions. So let's call it V. And then this n vector here is a vector that if you would plot it, it makes a 90-degree angle with the plane. So if you take some crosscut, then it always is 90 degrees. It's orthogonal to the plane. So let's look at a couple of examples, because as I told you, you should always try to build a mental picture of what is going on here. So I'm going to do 3 examples. The first one is this. Say that we have two planes given, V1 and V2. So the first plane is x plus 2y plus z equals 3. So that is like one sheet of paper somewhere in the plane. I do not really care where it is. I do not try to make a plot here, because to make an accurate sketch here, that's quite difficult. And then I have a second plane with equation x minus 4y plus 3z equals 5. And then it is given, so here I have two planes, and it is given that they intersect. So that means that they have to intersect in a line. And the question here is to find that line. So it is given that they intersect because, as you know, if you have two planes, they could be parallel. And if they're parallel, they don't see each other and they don't intersect. So here it is given that these two planes intersect in a line. And we would like to find an equation for that line. Okay. So what I am going to do, there are several approaches here, but the basic idea is the same. So I have a plane, let's say like this. So this is V1. I'm just sketching it. This is just two planes that I'm sketching. I'm not trying to be accurate here. And I have a second plane that goes approximately like this. So this is V2. And then as it is plotted here, I see that they intersect here and they intersect here. And then basically they intersect in a line L. And we would like to find an equation for this line. So what I'm going to do is I'm going to free the x in both of these planes. So for V1, I can rewrite the equation a little bit. And I'm going to write it as x equals 3 minus 2y minus z. Similarly, for V2, I'm going to write x is 5 plus 4y minus 3z. And now, if I want these two planes to intersect, then the x coordinates should be equal. So for the intersection, I have that 3 minus 2y minus z should equal 5 plus 4y minus 3z. z. So let's see if I solve this equation for z, then I can move all the z's to the left side. So I'm going to move this to the left side of the equation and the rest to the right side of the equation. And we see that apparently 2z equals 5 minus 3 is 2. I have plus 4y plus 2y equals plus 6 times y. So apparently z equals 1 plus 3 times y at the intersection, at the whole line there. Now, for x, I still have these two equations, so let us use the top one here. So I have that I can write x as 3 minus 2y minus z, which apparently equals 3 minus 2y minus 1 plus 3y. That is what I just found that holds at the intersection. And 3 minus 1 equals 2 minus 2y minus 3y is minus 5y. So I have now found, so conclusion, is x equals 2 minus 5y, z equals 1 plus 3y, and y can be any number that you pick. So this is a line, though it may look a little bit different from what you're used in two-dimensional space, y equals mx plus b. We have here a line in three-dimensional space, because as soon as you give me a number y can be any number, I can compute x and z, and then I have a point in space. So I now have a whole bunch of points in space given by these three equations here. Now, you might say, or you may not say, I would like to have this as a vector equation, because we have seen that you can describe lines in space by vector equations. So let me grab a bit more paper. So we have, let me copy the conclusion to this bit of paper. Copy, paste. So you could also say, well, I would like to have to see more clearly that this is a straight line. So what I'm going to do is that I'm going to say, well, x, y, z, that's how I normally describe a vector equation, a line as a vector equation. Well, that's 2 minus 5 times y, 1 plus 3 times y. And now maybe you already see that it is a little bit like a vector equation, because this is 2 plus y times minus 5. Let me do it slowly. The second line I can write as 0 plus y times 1. And the last line as 1 plus y times 3. And now I'm kind of deconstructing it into the form, this is the vector 2, 0, 1 plus y times minus 5, 1, 3. And y can be any number. And before we called that lambda. So you could also say, well, this is the same, since y it can be any number, as x, y, z equals 2, 0, 1 plus some number lambda times minus 5, 1 and 3 with a lambda any number. So this is the standard vector equation for a line. And this line is the intersection between the two planes. You can easily check that. So this point that we have found here, this 2, 0, 1, you can easily verify that it is in both of the planes. And in fact, if you would substitute all these coordinates into the equations of the planes, they should hold there. Because, well, we have one plane, we have another plane, they intersect in this line, which means that the line L is in both the original planes. So this solves this question. So that was my first example about what we have seen last week. Next one is, given a plane and a point, find the distance between them. So here, let me check. Yep, okay. I first would like to do another one, sorry about that. I'm first going to do this question. I was a bit confused because the order is different than what I have here. I like to do it in this order first, that makes more sense. So this is from an old midterm test, so you could have this question in week 5. Probably we'll make a version or a different one, but this could be a question that you would have during your midterm test. So given here is a line through 2 points. So you can imagine that, right? It always is good to make a mental picture here. So I have 2 points in space. And as you know, there's exactly one straight line that goes through them. So if I give you the points 4, 0, 4 and -2, 1, -2, then you know that there's precisely one straight line that goes through both of these points. Then we also have a plane, and it is given again that L intersects V, so that the line intersects the plane. So we have a plane in space, we have a line, and they intersect. That is not always true. It can be that they're parallel and then they do not have an intersection point, but here it is given in the question that they intersect in a point, and let's call that point P, it says. And the question is, find P. Now, if you would have to do this without much mathematics, then you can imagine that it's quite complicated. To try and plot this, what's going on here, that's quite difficult. It will turn out that if we use what we have seen last week, that this is not a particularly difficult question. So I'm going to do it in a couple of steps. So I have to subdivide it in a couple of steps. So step 1, I'm going to find an equation for this line L. So find an equation for L. So I should have a point on the line. Well, I have 2 points that are on this line, so I can pick either of them. So let's pick the first one, 4, 0, 4. And I have to choose a direction vector. And given 2 points, and you want a line that goes through them, the direction vector, you have to subtract those 2 points from each other. So the direction vector, so I need 2 things. I need a point. And I'm going to take 4, 0 and 4. And I need a direction vector. That's what we have seen last week. Direction vector A. And to find A, I just subtract those 2 points. So 4, 0, 4, that's 1 point on the line, -2, 1, -2. And if you do that, then you get 6, 1 and 6. 6 -1, sorry, and 6. I hope all of you shouted at your computer, -1, not 1. That will be good. So now we have all the ingredients. So L has vector equation x, y, z equals 4, 0, 4 plus lambda times the direction vector, and the direction vector is 6, -1 and 6, and lambda can be any number. Now, next what I would like to do is find the intersection point of the line with the plane. So that's going to be step 2. Step 2. Find intersection point of L, the line, and V, the plane. Now, what I would like to do, so the main idea here is if you need the intersection point, what you do is you substitute the coordinates of the line into the equation for the plane V. So that is what we will do. And to do that, it is a bit easier to write the line as x is 4 plus 6 lambda, y equals 0 minus lambda, so y equals minus lambda, and finally z equals 4 plus 6 lambda. So that is just this vector equation, but then written in the components. And now what I'm going to do is plug in these x, y, and z values into the equation for the plane. If you do that, you get an equation with only lambda, so I can solve for lambda. And once I have a value for lambda, I can compute x, y, and z, and then I have the point P. Question answered. So let's do that. So I have the plane, and the plane has equation. So V is the plane 4x plus y minus 5z equals 17. L can apparently be written as x equals 4 plus 6 lambda, y equals minus lambda, z equals 4 plus 6 lambda. I'm just going to plug that in, and you find that 4 times 4 plus 6 lambda, so that's 4x, plus y plus minus lambda, minus 5z, minus 5, 4 plus 6 lambda equals 17. Now, if you solve this for lambda, I did it on a piece of scrap paper here, you will find, I'm sure you can do that, so I'm not going to do all these steps here, you'll find that lambda equals minus 3. You can check that yourself. And then step 3 is compute L. Compute P, the point. So x is 4 plus 6 times minus 3. Y is minus lambda equals 3. And z equals 4 plus 6 times minus 3. And of course you see that both x and z are equal, and they 4 minus 18, which is minus 14. So we're done now, because this was the question, what is the intersection point of the line and the plane? So the point P equals minus 14, 3, minus 14. And again, that is one of the nicer things about these types of questions. You can easily check this, right? So you can check whether P is indeed on your line L and whether it's also in the plane. So if you plug it into the equation for the plane, you should find that it satisfies that equation. So if you compute 4x plus y minus 5z, you should find 17, because the intersection point should be both on the line and in the plane. Okay. Great. Now, last week, at the very end, I talked about the distance between a point and a plane, and I derived a standard formula for that. And as I already told you, the standard formula, you can learn it by heart. I don't know it by heart, because I like to solve them in a different way. And that's also what I would like to show. So that's going to be my last example on the theory from last week. So again, there is a standard formula for it and you can use that. If you like that, fine with me. I'm going to solve it a little bit different here. So instead of using that standard formula, I'm going to see what's actually going on here. So it says given a plane, so again, we have a plane. We have a point, so a point somewhere in space. Find the distance between the plane and the point. So what would that be? Well, if you would draw a straight line that makes a 90-degree angle with the plane, so a vector perpendicular to the plane that goes through this point here, and then where it intersects with the plane, that distance. If the point would happen to be in the plane, very special case, the distance is 0. So that's not very likely that it happens. So again, if I make a little picture, I have a plane V. So this is a plane. I have a point P. And now my idea, how I'm going to solve this, is that I'm going to take the line perpendicular to the plane through the point. So the line here that goes through the plane and it continues again here. So this is a straight line L. And L is L is perpendicular to V. So it makes a 90-degree angle, it is orthogonal, whatever you want to do it. You could also L orthogonal to V. Now, you may think that this is difficult, but it's very easy to construct this line. Because what do we need for a line in space? Well, we've already seen that. We need a point on the line. Point on the line. Well, that's very easy, right? Because P should be on the line. So I'm going to take P, 18, 11, 19. And I need a direction vector. So what I'm going to choose as a direction vector is a normal of the plane. So the direction vector A equals n, where n is the normal to the plane V. And as you hopefully recall, if this is the equation for the plane, I can immediately see a normal, because I can just read off the coefficients and I can see that n equals 4, 3, and 4. The coefficients of x, y, and z in the equation for the plane. So apparently, this line L is all points x, y, z that can be written as 18, 11, 19, a point on the line, the point P in this case, plus any multiple of the direction vector, which is 4, 3, and 4. And lambda can be any number. Now, you may wonder, how does this help us? Because I haven't solved the original question yet. I don't know the distance. So now I have an equation for V, I have an equation for L. Now, what I'm going to do is basically what I did in the previous question. I'm going to find now the intersection point here of the line and the plane. So I'm going to call that S. And the distance from P to the plane is the distance between the points P and S. So let me write that down. So then we have that the distance between P and V, so point and plane, equals the distance between P and S, where S is this intersection point. And the distance between 2 points, that's easy, right? You take the difference of the x coordinates, of the y coordinates, of the z coordinates, square them, add them together, take the square root. The normal formula for the distance between 2 points in space. So basically we're done now, because now we're back to the previous question. So step 1 was to find an equation for L. So let me squeeze that in here. So step 1, find L, this line. I'm going to add a page. And step 2 is going to be compute the intersection point. So step 2, find S, intersection point of L and V. Now L, we have just found, can be written as x is 18 plus 4 lambda, y is 11 plus 3 lambda, z equals 19 plus 4 lambda. The equation for V is 4x plus 3y plus 4z equals 17. So take these and plug them into that equation. You find an equation for lambda and you solve for lambda. So I'm not going to do all those steps in between. I'm sure you can do it, and otherwise ask me. And this is going to give you that lambda equals, what do we find? I did it on a bit of scrap paper, minus 4. So what we find with intermediate steps that I'm not showing here because I've already done them in the previous example is if you now compute what S is, the intersection point, you would find 2 minus 1 and 3. And then the last step, step 3, the distance between our point and the plane is the distance between our point and S. And if you compute that carefully, you will find an ugly answer because it's going to be 4 times the square root of 41. You can check that yourself. This is just computational stuff. That's just standard simple computations. Okay. So that concludes the bits that I wanted to add to what we have seen last week. So a couple of examples, and hopefully this will help you solve the other questions that are in the homework and in the online test. Try to do all the homework. In ONS we can see how you're doing on the homework, which is pretty good. So most of you are actually working there. Some are a bit behind, but try to solve these problems. It's the best preparation you can do for all the tests, to do both the homework and the online tests. So you have to try and solve these things yourself. If you get stuck, ask a fellow student, ask your tutor, ask me. And we'll try to help you get along, okay? So let me see. So here I'm going to take a little checking of the chat room. There will be solutions of Smith and Minton, so we will provide you with solutions there, so you get answers to the questions. Of course, after you've handed in your homework, and you can also see the solutions in ONS. How do you eliminate lambda and mu? That's one of the things that I indeed wanted to show you. So let me go to the notes from last week. No, I need, sorry, if this... Okay. So here, I still wanted to do that. If you have an equation for a plane, like here. So as I said, this is what is called a vector equation for a plane. And hopefully you can see how this works, because you take all points x, y, z. You start from a certain point and you take multiples of 2 sort of direction vectors there. Now, how can you get from this equation to this equation? That's something that I would still like to show you. So let me get some paper. This one. And I'm going to start with the vector equation. And then I'm going to rewrite it to get to the standard one. So like I've already done for the line a couple of times, I can take this vector equation and I can write it out in components. So I'm going to write it as x equals 1 plus lambda plus 3 times mu, y equals 2 plus 0 times lambda, I'm not going to copy that, plus 4 times mu. And then finally z, I'm going to squeeze that in here, hopefully you can read it. I'm going to copy it to the next slide in a second, is 3 plus lambda plus 5 times mu. So that is the vector equation, but then written out in the 3 individual components, in the components for x, y, and z. So now what I'm basically going to do to get to like the normal equation, the equation where you can read of the normal, etc., is the following. Oops, like this. So what I'm basically going to do is get rid of the lambda and the mu. So if you take the first equation and you subtract the last equation, then what you see is that x minus z is 1 minus 3, so that's minus 2. Minus 2. The lambda drops out, that's why I take x minus z. I want the lambda to drop out, and I have 3 mu minus 5 mu, which is minus 2 mu. And on the other hand, I'm going to copy the equation for y. And now you see that if I take 2 times the top equation and then add the last equation, so if I take 2x minus 2z equals minus 4 mu, and the reason I multiply this equation with 2 is that I want there to be a minus 4 mu, because now I also have the equation y equals 2 plus 4 mu. And I'm simply going to add these two equations. So what we then have is that 2x plus y minus 2z equals minus 4 plus 2 is minus 2. And the mu drops out. And this is the equation that we wanted. So here you have like the standard normal equation for a plane in 3-dimensional space. And if you want, it's not being asked here, but now you can immediately read off that apparently a normal to this plane is 2, 1, minus 2. The coefficients of x, y, and z. Okay, so that's how you get from vector equation to usual equation, normal equation. So, okay. Then Jana also has a question in the chat room. If you always have to add like I did, let me write it in a different color. So for lines, I always wrote this, and maybe for a plane, I also added this lambda in r, mu in r. It is nice to write it. It is not strictly required always, but you make immediately clear that it's like a free parameter, that it can have any value that you would like it to have. So it's good to do so. Not completely necessary, but better be on the safe side there. Okay, so that wraps up for this moment. my talking about the week 2 material. And as I said, I know this is a lot and many of you find this difficult. So that's also why I did a lot of, spent quite a bit of time on it today. But still, if you have further questions, let me know. Just put them on Canvas or send me an email, send me a message, and I can even spend time on it on Wednesday if you want. So if you get stuck during the question hour, doing the homework, online questions, etc., just let me know, okay? So let me make a little start with the material for this week. So let me switch to the presentation here. So we're going to week 3 now. So as you see here, it says on week 3 here on the title slide, limits, continuity and differentiation. And if I know you a little bit, then probably limits, you either say, what is this? Or you get goose skin if I start talking about it. Same for continuity. Differentiation, in my experience, is something that you've done so much in high school that you're completely fine with that. So we go to do a recap of differentiation, but that's the differentiation. Just finding the derivative of a function that you know how to do, is you're familiar with, and that you've practiced a zillion times. Limits, continuity might be a little bit new. They're a bit theoretical concepts. They're necessary for what we will be doing next. So differentiation has many applications. Differentiation, for instance, if you want to maximize profits, minimize costs, stuff like that, you will always use differentiation. And limits and continuity are basically steps to get there. Along the way, I'm going to try and give you nice examples and convince you why this is important. So I'll do my best with a bit of hand waving, showing some applications. Hopefully, a bit of fun that will make you study this without too much boredness. So one of the ways I do that is by going to present you a cat video. So I'm not sure, but probably this is the first time, maybe also the last time, that you will get to see a YouTube cat video during math classes. So let's see. I should switch here and then. Okay. So sections in the book, quite many, but as I said, many of them are on differentiation, and you already know how to do that. So sections from chapters 1 and 2, the application. So I'm going to talk about the cat, and here, as I spoiled a little bit, we're going to look at a cat's pupils. They're quite interesting. A bit on a parabolic reflector, tell you more about that, and a bit on traveling by train, which I used to do every single day from Utrecht to Eindhoven, and now it's like once a week. And here are the topics, so let's not pay too much time on that for now. So first, let's look at a cat video. So what I would like you to pay attention to here, sound in the video is not important. This cat is watching a cartoon on television. And as it is watching the cartoon, what you will see, let me lower the sound a little bit because I'm not sure if I'm going to run into YouTube copyright problems. I don't want that, so I also keep talking. What you see is that the pupils of the cat, they become bigger and smaller. And I want to spend a little bit of time on that. So usually when it gets dark outside, your pupils get larger. And when there's very bright sunlight, they get smaller. So your pupils somehow manage how much light you take in. Of course, the cat is reacting to the video and it gets into predator mode, and that's why the pupils change size. But in principle, as a kind of simple model for how this works, you could look at the size of the pupil and then see that as a function of how much light there is. So you can, of course, measure how much light there is outside. So let's say that we have a function f of x here. And then f is the diameter of the pupils. And this x is some measure for the amount of light you have outside. So it's bigger equals 0. When it's completely dark, x equals 0. When x goes to infinity, there is much light, it's bright sunlight. And now what we would like to do is find the diameter of the pupil for minimum light, so going to 0, and for maximum light, basically x going to infinity. So what you see here is a plot that I made. And in the plot, you see, you can sort of read off what the diameter of the pupil is for minimum light and maximum light. But what I wanted to emphasize here is that you cannot simply plug in, for instance, x equals 0 into this formula. Because if you look at the formula, then what you see is that it has an x to the power minus 1 half. Now, of course, x to the power minus 1 half, so x to the power minus 0.5, that's 1 over square root of x. You cannot plug in x equals 0 there, because then you have division by 0 and all kinds of disasters happen. But still, if you look at the plot here that I use the computer to plot here, you see that it goes to 40. And similarly, also x becoming very, very big, that's also hard to do with this formula here. Because I would like to plug in x is infinity, but x is infinity, that's not really a value. But clearly you see that if you make x bigger and bigger, that the diameter will go to 6 millimeters. So how can we deal with that mathematically? Well, to talk about that, we need the concept of limits. So that is going to be our first topic. We would like to talk about the limit of x going to 0 and the limit of x going to infinity. So we need some notation how we can deal with that and how we can do mathematics with that. So at this point, let's have a 15-minute break and I'll resume lecturing at 14:30, so at 2:30, and I'll see you in a bit. So let's start again. I hope you had a nice break and maybe even got a little sunshine. It's beautiful weather outside. Before the break, we were talking about this function here, y is f of x. It has this funny form. And we were discussing why it is interesting to consider this for very small values of x close to 0 but not equal to 0, because if x is equal to 0, you cannot apply this function, it's not defined. And also for x going to infinity, getting very large values. So the diameter for minimum light would be f0, but it's not defined because you get division by 0. And the diameter for a maximum light intensity fx for very large values of x. Those are interesting. So let's first consider the case where x is very close to 0. So we want to have a mathematical way of saying that x gets closer and closer to 0, but not equal to 0, because it cannot be equal. For equal, you would get division by 0, not defined. So the notation we have for that is what is in this box here. The limit of x going to 0 of fx. So that is the notation that we use, that we would like to take x very close to 0, but not equal to 0. Now, and there is a trick, and this is mathematically sound and very strict. So the way it is described up here, that is not very mathematical. That is a bit of hand waving, but that's the intuition you should have of what it really means when you're working with it and when you're thinking about it. And this here is very, very dry. There is no opinions in there. There is no hand waving. This is very strict. So what we write here is the limit of x going to 0 of fx. And then we just plug in the formula. And here you see a trick that we can do. So I'm going to multiply both numerator and denominator with square root of x. Since x is close to 0 but not equal to 0, I can do this. So there is no division by 0, and I'm basically just multiplying with 1 when I do this. Now, if you work that out, you get this formula here. And you see that now, at this moment in time, there is no problem if we plug in x equals to 0. So now I can just fill in x equals to 0. So I do that. And then once you do that, you can forget about the limit. So you can move it away and you just replace x by 0. And then you can compute whatever it says there. So now it says 160 over 4, which is 40. So apparently that is the diameter for minimum light for x going to 0. Similarly, we can also, in minimum light, the pupils have a diameter of 40 millimeters, which is 4 centimeters. So apparently this is not a cat, it's more like a T-Rex, I guess. Let's immediately go to maximum light. So for maximum light, we would like to let x go to infinity. So we take very, very big values of x without specifying what it is. It can be 1,000,000, 1,000,000,000, 10 to the power 12 or whatever. Very big values of x. So the way we write that is like this. The limit of x going to plus infinity, fx. And here we have a similar treatment. So again, we write the limit of x going to infinity fx. We plug in the formula. And what we use now is that if you have 160 over the square root of x, and x is going to be a very, very big number, then also square root of x is going to be a very big number, because the square root function, as you know, does, let's do it like this. If you have x, y, then the square root function looks something like this. So if x is going to infinity, then also square root of x is going to infinity. And then if we divide by it, like we do here in the formula, 160 over the square root of x, that's going to 0. So I can immediately write it as 0 plus 90 over 0 plus 15, which is 6. So apparently that is the diameter for x going to infinity, the function for x going to infinity. Okay. So that concludes the kind of intuitive idea that you should have for limits. Here we have something similar. I'm going to take f of x is sine of x over x. And if you think a little bit about this, then you see that this is not defined for x equals 0, because there would be a 0 in the denominator. But there is also a sine of x here, which also goes to 0 for x going to 0. So then it's going to be a kind of rat race. Who's going to win there? Who's going to 0 fastest, the numerator or the denominator? Now, if you plot this function, I've done that here using some computer software, then it looks approximately like this. And if you would zoom in here, you would see that you get closer and closer to 1. So probably the limit equals 1. And indeed, if you plug in values, so if you approach 0 here from the left, and you take, well, minus 1 over 10, minus 1 over 100, minus 1 over 1000, and you compute the function values, then you see that they get closer and closer to 1. You could also do that if you move to 0 from this direction, and, well, you immediately see that if you compute f of minus x, that is sine of minus x over minus x, which is minus sine x over minus x, which is f of x. So you get a very similar table, of course. You see that also if you take 1 over 10, 1 over 100, 1 over 1000, you get the same values basically. So what you might think here, and indeed that holds true, we'll see this is a standard limit, this function here goes to 1 if x goes to 0. Now let's try to formalize this a little bit. So what does it mean? So that's section 1.2 in the book. So an informal definition of limit. If you write something like this, what it means is that you can make f of x as close to L as you like by choosing x very close to a, but not equal to a. And that's in italics here, because that is very important. X is not going to be equal to a, but very, very close to a. And the way you pronounce this, the way you read this formula, is the limit of f of x as x goes to a equals L. So that's how you would read it if you would have to read this formula. Limit of f of x as x goes to a equals L. And the meaning is that you can get arbitrarily close to L if you choose x very close to a. A little generalization here is just a picture, but here you can see that it matters if you go to 0 from this direction or from this direction. So if you would be coming from the left and you would go along this curve, you see that you end up at 2. And if you come from the right, you get closer and closer to 0, you end up at minus 1. So the way we write this is that we have this notation here. X is coming from below, or x is going to 0, and then there is a superscript minus. And the superscript means that we get values of x close to 0, but a little bit to the left of 0. And from the graph, you can see that it equals 2. And of course, you can also do that from the right, and then we write a downward pointing arrow, or we use the notation 0 plus. So both of these notations are fine, and it depends a little bit on the textbook or the online question system, which notation they use. Mathematicians use both. Depends a bit on the country you're in and so on. It's not standardized. Now, this is just definition. If these one-sided limits, so one-sided means either from the left or from the right, if they're not equal, like in this example, then we say that the limit does not exist. So for the limit to exist, we want both of these to be the same. And that's in the blue box here. If we just write limit, so a general arrow without coming from the left or from the right. If this equals, so if you write equals L, it means it exists and is equal to L. That means that if we come from the left or we come from the right, both of these values should exist, should be equal, should be L. Now then, if you have a polynomial, we've already seen polynomials are very nice functions. They're always defined and so on. So if you have a limit of a polynomial, you just plug in the value. It always exists. You could just plug in x equals a and you're done. So the limit notation only has meaning if special things happen, if your function does not exist at the point a itself. Now, that can already occur at rational functions. So we have seen like we go from polynomials to polynomial over polynomial, like we have here, p over q. And we have seen that if the denominator would get 0, then stuff can happen, interesting stuff. So here we can already talk about limits. Now, two cases. Case 1 is if q of a is unequal to 0, you can just plug in x equals a, you're done. The second is a bit more interesting. So if q of a equals 0, that's the more difficult case and different things can happen. So let's look at a couple of examples, and I'm just going to write them here on the slide. So let's divide this into two parts. And I am going to consider, for instance, the limit x is going to 2, x over x minus 2. Well, if you would plug in values here that are quite close to 2, so you choose x close to 2 but not equal to 2, so 2.1 or 2.001 or 1.999, and you plug that in, then you immediately see that you get very big values here. So this does not exist. It gets arbitrarily big, the expression, if you have very values of x close to 2. Now, what can also happen is that we have something limit x is going to 2, x squared minus 4 over x minus 2. And if you look at this a little bit longer, then you see that we can rewrite this as the limit x is going to 2, and in the numerator you can write it as x plus 2 times x minus 2. We divide it by x minus 2, and now you see that we have this factor x minus 2 both in the numerator and denominator. Since x is close to 2 but never equal to 2, I can divide by this thing. And then what we see here is that basically we get a new limit, and that is the limit x is going to 2, x plus 2, and then I can just plug it in because this is very well defined, and we find 4. So here the limit exists and is equal to 4. Now, what could also happen, one more example. If you look at the limit of x going to 2, x squared minus 4 over x minus 2 squared, then you see that we can simplify it like before. So I can write this as the limit x is going to 2, x plus 2, x minus 2 over x minus 2, x minus 2. Like in the previous example, I can divide both numerator and denominator by x minus 2. And what we end up with is the limit x is going to 2, x plus 2 over x minus 2. And now if you plug in values of x close to 2 not equal to 2, so 1.999 or 2.001, you see that the numerator gets very close to 4, denominator gets very close to 0, and this whole thing does not exist. Does not exist. So all kinds of things can happen here, and the only situation where you can be kind of saved if the denominator equals 0 is if the numerator is also equal to 0. That's what we've seen in the second example, because then we could divide out this x minus 2 factor. But it does not always work, because as we have seen here, we could divide out this x minus 2 factor, but there was yet another one in the denominator, and the limit still did not exist. So if you have these quotients, rational functions and limits, you really have to look what's happening there, and maybe it exists, maybe it does not exist. Okay. There is one type of limit that you will see a couple of times, both in the online questions and in the questions in the book, which is limits with roots. Well, this is the general thing, that if you have a limit of a function, then the nth root will also be the nth root of the limit, okay, for what it's worth. But there is one type of questions like this. If you have an expression with 0 divided by 0, you can try to rationalize, is what it says here. And quite a few of you are Dutch students in Dutch language. The trick that I'm going to show now is called worteltruc. So in English, the literal translation would be the square root trick. And it works like this. So say that we have an expression like this. Square root of x plus 2 minus square root of 2 over x. And the limit is going to 0. Now, if we check what's going to happen here in the numerator, if we just plug in x equals 0, we would get square root of 2 minus square root of 2 equals 0. Denominator is also 0, and 0 divided by 0, well, all kinds of interesting stuff can happen. That's basically the main message of the previous slide. Now, what we're going to do here is we're going to look at the numerator, and we're going to multiply with a similar expression, but then with a plus sign. And the idea here, so the reason I do this, is that I have a minus b. So that's here, this is a minus b. And I'm going to multiply that with a plus b. But if I have an expression and I multiply the numerator and I don't want to change it, then I also have to multiply the denominator with that. And the idea is now that in the numerator it says a squared minus b squared, because the minus ab and plus ab cancel. And due to this effect, what I get is this thing squared minus this thing squared. So what I get there is x plus 2 minus 2. So basically we have a is square root x plus 2 and b is square root of 2, and then a squared minus b squared equals x plus 2 minus 2 equals x. So x plus 2 minus 2 equals x. There is also an x here in the denominator. They cancel out. And with all these intermediate steps, basically my limit boils down to this expression here. And now this expression, this one is okay to plug in x equals 0. So that's what we do when we get 1 over 2 times square root of 2. So that is what is called in English rationalizing, and in Dutch language the worteltruc. So the square root trick, whatever you want to call it. So if you see expressions of this type here, think of this trick. There is one more version of it, and that's the next example. And here it is a little bit hidden. So we have the limit x going to 25, x minus 25 over square root x minus 5. If you have a limit, first you try to plug in the value. So we just try to plug in x equals 25 and we get 0 over 0. Now, all kinds of things can happen. And here, what I'm going to do is multiply the denominator, so square root x minus 5. I would like to multiply it with square root of x plus 5. Same idea. I have a minus b, I multiply with a plus b. And if you do that, you get a squared minus b squared, and here that's x minus 25. Now, if you do that, if you multiply denominator with this factor, you should also multiply the numerator with that number. So I'm going to multiply the whole expression with square root x plus 5 over square root x plus 5. I'm just multiplying with 1, and you can do that. That's okay. You don't change something if you multiply by 1. Then in the denominator, if you expand this, you get x minus 25. You can strike these two, and you're being left with this limit. And at every stage, after every algebraic manipulation that you've been doing, you try if you can substitute x equals 25 and if it exists. And here it exists, so nothing goes wrong here. So we get square root 25 plus 5, and that equals 10. So be prepared for these types of limits. You see quite a few of them. And if you haven't got a clue what to do, they can be quite nasty and it can be quite difficult to see which trick you should try. So if you see something like a plus b, multiply with a minus b, or if you see a minus b, multiply with a plus b and see if it gets simpler. And for limits, if you compute a limit and you get something like plus or minus infinity, then we say that the limit does not exist. So we only say that a limit exists if we have something like really the limit x is going to a f x equals L, and L is a number. Infinity minus infinity are not numbers. They're not in the real numbers. They're not in R. Then we say that limit exists. And if you find plus infinity or minus infinity, we say that the limit does not exist. That was an answer to a question from Alec in the chat box. Okay. Now, you will be doing plenty of limits. So if you run into trouble, let me know and I'll do more examples. The standard functions, so if you have functions like sine, cosine, exponential function, logarithm, you can just take them. So as long as this a here is in the domain of your function, and that's only something special for the logarithm here, you can just take the limit. So you just plug in the x value. One more interesting theorem, and it looks very complicated here on this slide, but basically this picture tells it all. And I'm going to do a couple of examples in a minute. So this is called the squeeze theorem or sandwich theorem, and there was a couple of versions of it. And it goes like this. If you would like to compute, so what we would like to find here is, so the question is basically to find the limit x is going to a of g of x. And g is the blue function in the graph. Now, if g is complicated and we cannot immediately see what the value is, maybe we can squeeze it in between two other functions. So I'm going to try and find a function h and a function f, such that one is always above my blue graph, one is always below my blue graph. And then if I can easily compute the limit of f the lower bound, and of h, the upper bound, and they are equal, then the g function also has to go there. So basically what you see here in the picture, we have this red graph, and it goes to a certain L if x gets very close to a. The f graph also goes to L if x goes to a. Then the blue one doesn't have any space because it's squeezed in between f and h. It also has to go there. So sometimes this is also called the two policemen and a drunk theorem. So you have a drunk on the street, there are two policemen, they pick him up, and there is one policeman to one side of the drunk, the other policeman to the other side of the drunk. Then if the two policemen go to the police station, the drunk also has to go to the police station. So that's the idea that you can have with this. So the two policemen and the drunk theorem, or the squeeze theorem. So how does that work? So let's see. Say that we have this function here. So I'm being asked to compute the limit x is going to 0, x squared times the cosine 1 over x. Now, this is hard to do, and there is no standard trick or manipulation to get rid of this cosine 1 over x thing here. And of course, if you try to plug in x, it's not going to work, because 1 over x, if you plug in x equals 0, that blows up. And then you get the cosine of a very big number, and well, we haven't got a clue what it is, because the cosine happily goes in between -1 and +1. That's one way to look at it. The other way is to say, well, indeed, the cosine is always in between -1 and +1. So it cannot have very big values. Then if you multiply with x squared, if x is going to 0, then x squared is going to 0. And if you multiply that with some number in between -1 and +1, probably that limit goes to 0. So the squeeze theorem is a way to make that sound, this argumentation. So let's see. Here I plotted the graph, and of course I only plot the graph here to illustrate for you what's going on here. You don't need the graph, but I'm trying to explain it here, so that's why I give it. So we have this function, g of x. So the drunk in the theorem, the middle function, is x squared times cosine 1 over x. Now, I'm going to notice that the cosine is always in between -1 and +1. So we have -1 is less or equal, also cosine 1 over x is less or equal 1. Now, if you multiply the whole expression with x squared, because I want to end up with this thing here, and I only have this now, so I multiply the whole equation with x squared, which is a positive number, so I can do that. Then, basically what I've done is given an upper bound and a lower bound, because this minus x squared here, that is the black function, which is the lower bound here. And then this plus x squared here is the red function h, which is the upper bound here. And what you see is that our blue graph always goes up, down, up, down, up, down, and very wildly close to x equals 0. But it's always in between the red and the black curves. Now, for the red and the black curves, I can easily see what the limit is if x is going to 0, it's 0. So then we use the squeeze theorem. And so we have limit x goes to 0 fx equals the limit x going to 0 hx, and both of them are 0. And then the squeeze theorem tells us that the middle function g of x should also go to 0. So that's the way this works. Let's do one more example. Sine of 2x over x. And now pay attention, we have x is going to infinity. So that is quite complicated, because x is going to infinity. I haven't got a clue what this sine of 2x is going to do. Because, well, the sine function always goes in between -1 and +1. And, well, this, if you would just have this expression here, so without the 1 over x, it doesn't exist, because the sine function just goes in between -1 and +1, so I cannot say anything about this. But here we're good, because this sine function is in between -1 and +1. So I've plotted it here. So here is g, the middle function in the squeeze theorem. I'm going to be using the squeeze theorem. So that's the blue function. like before, I'm going to use that the sign is in between -1 and +1. I'm dividing by x to get to what I have here. And that basically gives me my lower bound and upper bound. So the black and the red curves. For the black and the red curve, so that's -1 over x and 1 over x, I know what happens if x goes to infinity. If x becomes larger and larger and larger, they go to 0. So apparently the blue graph, and we could already have seen that here, also goes to 0. So f goes to 0, h goes to 0 for x goes to infinity, g goes to 0. So that's the way this works. That's the squeeze theorem. Okay. So that's great. So we're doing pretty good here. Let me see if there are any questions at this moment. Are we going to have limits which can solve only with DLH? What is DLH? I'm not sure I understand your question here. If you want an answer, you should elaborate. It says here, does the squeeze theorem only work for cosine and sine functions? No, there is more examples there. But I would have to think. I do not have one straight at hand, but probably you will see more in your homework and online questions. L'Hopital. So DLH is L'Hopital, thanks. We will be working with L'Hopital too. So we will treat L'Hopital's theorem in a bit. And there are going to be integrals that you can solve with L'Hopital. If you know anything about Taylor series, I'm a bit reluctant to say that, but if you have seen Taylor series before, you can also use those. So that's fine, but Taylor series is not a part of this course. So we will be doing them using L'Hopital. And with the theory during this calculus course, that will be the only way to solve them then. Yeah. Okay. So we have a bit of time left. So let me start with section 1.4 of the book. Not because we're in a hurry, we're pretty good on time this week, but I expect that you may have questions for the Wednesday lectures. So as I told you, I'm happy to deal with anything that you have questions about. Just let them know and I'll spend time on that on Wednesday. I also plan to use something like Mentimeter to make it a little bit interactive and see how you're picking up stuff, and if you have particular questions, or maybe I can go ahead more quickly because you already know how to do that. But I didn't prepare anything of that yet, so maybe next week. But if you have questions, if you're going to solve the problems, and even though the weather is going to be very nice today and tomorrow, spend time on calculus. It's really important to keep working. And if you run into trouble, let me know, and I'm happy to spend time on questions from week 2 or this stuff. Fine with me. So, next topic, continuity. So, we have limits. Now we're going to use them to look at continuous functions, and then we're going to look at differentiation. And differentiation is really important. As you recall, differentiation you can use if you have a function to find maxima, minima, and you can do all kinds of useful stuff with them. And we will be doing that too. So we have plenty of examples on that. Before that, continuity. So as I try to convey to you many mathematical concepts, I can just give a definition in a blue box like this. But it makes much more sense if you know the idea behind them. So in mathematics, we introduce stuff, we make definitions and say, well, we would like to call a function continuous. There is always a reason for that, why we do that and why we want to deal with them. So continuous function, so the intuition you should have there without any formal definition, just what you should think of is if you would draw a function, you would draw the graph of the function. If you can do that without lifting your pen from the paper, then it's continuous. So, for instance, this is a continuous function because I can start here and I can just draw this function. Now, it makes sense to look at a couple of examples where this is not true. If you know what not continuous is, that can help you understand what continuous is. So this thing is not continuous because I come from the left here, I'm drawing this, and then I have to jump. So I have to lift my pen from the paper to draw the rest. So it has a jump, and a function that has a jump that goes from one value to another value, that is not continuous. This is also not continuous because if you look carefully, here is a little open circle, and a little open circle means that this point does not belong to the graph. But it's very artificial. As you can see here, I could just as well draw a line, a curve through this, so I can make this one continuous. So if you have a graph like this with just a hole in there, you can make it continuous. So in principle, it is not continuous, but this is really artificial. So if you think, many people like to have formulas for functions. In principle, if I give you just a graph like this thing here, you have a function, but many people think there should always be a formula with x and y's in here. You can give a formula for something like this. And what you could think of, but as I said, it is very artificial. Where do I have it? I have a little example here on my other screen. So I'm trying to find it for you. So what you could think of is something that we've basically already seen. So you could think of the function that is defined like this. So if you think of the function f of x equals x squared minus 4 over x minus 2. Then if we ask you what is the domain of this function, then the domain of f is every real number as long as you do not take 2. Because if you would plug in 2 into this formula, you would get division by 0, and that's not defined. But as I said, this is really artificial, because if you spend a little time on this, you see that x squared minus 4 over x minus 2, well, that's just x plus 2 times x minus 2 over x minus 2. And as long as x is not equal to 2, you can simplify this to x plus 2. And this expression, x plus 2, is defined for every single x. So if I would plot this function, I would get a graph that is, well, a bit similar to this thing. It's a straight line, but at x equals 2, there is a hole in the graph like you have here. So artificial, you can make it continuous. And we will see how that works in a bit. Okay. So continuous, not continuous because it has a jump, not continuous because there is a hole in the graph, but we can just plug the hole and make it continuous. And one more situation, the function is undefined, so it goes to plus infinity or it goes to minus infinity. That can also happen. So those are situations where your graph is not continuous, and when you have something like this, so sine, cosine, square root, every single polynomial, they're all continuous, they're all nice functions, and we will meet them in a bit. This thing, it can already happen with simple rational functions. If you have, the function that you see here is probably 1 over x, or minus 1 over x, I guess. Or if you have something like f of x is 1 over x squared minus 4, then you immediately see that for x equals plus 2 and x equals minus 2, you have difficulties, and you get these asymptotes like you see here. So those are functions that are not continuous. A function, so this is like the formal definition of what continuous means. And the formal definition, so the mathematical definition, not the intuitive one, the one from the previous slide, the one that is actually useful. If you have a function defined on some interval and you pick a point in that interval, then your function is continuous at that point if the limit equals the function value. And this, as I said, this is like the mathematical definition that you find in mathematical textbooks. And it is very short, but at the same time there is quite a bit of information in there. Because what this tells you is that the limit should exist, and also that the limit should be equal to the function value. So fa should be defined, the limit must exist, and the limit in fa must be the same. So all three of those requirements are in this definition. And then, if you want to say that a function is continuous on an interval, it means that it should be continuous at every point in the interval. Now, if I tell you continuity like this, then you probably think this makes sense. But there is something strange going on here. Because on the previous slide, I gave you a definition, an intuitive definition of continuity, where I told you that you should be able to draw the graph of the function without lifting your pen from the paper. Then if you look at this thing here, then I'm defining continuity at a point, which doesn't make sense at all if you think about lifting your pen from the paper, because you're only talking about a point here. And then to go to an interval again, like the intuitive definition uses, then I'm going to say, well, it should be continuous at all the points in the interval. So the mathematical description is a bit strange here. Okay. Let's do a little example and then we're probably done for today because it is almost 1:15. So I am going to do an example where we use this point definition of continuity. And let me write a little bit. So given is this function f of x. And very often people think that you should only have one formula to define a function, but that's not true. So you can have different formulas for every x value. So here I'm going to say that we have x squared minus c squared for x is less than 4 and cx plus 20 for x bigger equal 4, and this c is some number. So what this tells you is that we have something like this, x, y, and then at x equals 4 something special happens, because in principle to the left of 4 we have a parabola. So we have something like, let's draw that in red. So up until here. This thing could look something like this, x squared minus c squared, y equals x squared minus c squared. And to the right, it's cx plus 20. So that's something like a straight line. Something like this. Now, the question is, can I make these two curves connect? Can I choose c in such a way that this function is continuous? So find c such that f is continuous. Now, f being continuous, well, for every value to the left of 4, that's clear, it's a polynomial. Here also it's a polynomial. The only interesting point is to check whether f is continuous here. How can I make it continuous? Well, they should connect, these two graphs. So f is continuous at x equals 4 if x squared minus c squared at x equals 4 equals cx plus 20 at x equals 4. So what that means is that the red curve and the black straight line connect. So then we have 16 minus c squared equals 4c plus 20, which is equivalent to saying c squared plus 4c plus 4 equals 0, which is equivalent to saying that c plus 2 squared equals 0, c equals minus 2. So apparently my black line should have had a negative slope, but I didn't know that beforehand. So this is the way you can do that. And basically what we have required now is that the limit of f from the left and from the right should equal. So the limit from the left is basically if you go along this red curve, and then you would come up with 16 minus c squared. And from the right, you would find 4c plus 20, and the left limit and the right limit should be equal, and then you can define the function, you can give it that value, and then it connects there. So that's the way this works for a simple example. Let me stop for now because we've covered quite a bit here. If you have questions, let me know and I'll happily treat them on Wednesday. Don't forget your tutor meeting, please go there. Also, if you have no questions, go there because it's always useful to be there and discuss whatever you're working on and see how your colleagues are getting on. And I hope you have a great day and I'll see you on Wednesday morning. Okay, bye.